Hello, so in this video we will talk about linear congruences. So this means that we are talking about solving the equations of type Ax is congruent to B mod some number m. Okay. In order to do that, we first have to define a notation which is called the inverse in modulo arithmetic. So we'll say inverse modulo m. So A has inverse A bar such that A times A bar, this is congruent to 1 mod m. Okay. So but there is a condition. So condition is that the GCD of A and m should be equal to 1. In other words, A and m should be relatively prime. So let's write it down. A and m must be relatively prime. Okay. Now let's see whether we can use this information. Let's say we have a relation which says 3x is congruent to 5 modulo 7. The first condition is whether the GCD of 3 and 7 is 1 or not. So 3 and 7, the GCD is 1, we know that. Okay. So then this means that the inverse of 3 exists modulo 7. Now we have to find such a number when we multiply by 3 and then divide by 7, we get a remainder of 1, because that is what it means, that 3 times, for example, 3 times 4, 5, 3 times 5, this is equal to 15, right, which is, so 3 times 5, this is equal to 15 modulo 7, which is also equal to, congruent to 1 modulo 7. Okay. So this means 5 is an inverse of 3 modulo 7. Okay. Now what we do is we multiply by 5 both sides. So initially we had 3x is congruent to 5 modulo 7. So now what we do, we multiply by 5 here and we multiply by 5 here, again modulo 7. Okay. Now this 3 and 5, they cancel each other out, but because the product is 1, so we'll say x, this is congruent to 25 mod 7, and which is equal to 4 mod 7. So this means that all the numbers 4, 11, 28, 25 and so on are solutions of 3x congruent to 5 modulo 7. Let's check. So 3 times 4 is 12. 12 if divided by 7 gives us the remainder 5. 3 times 11 is 33. 33 when divided by 7 gives us a remainder 5, and you can check with all these numbers. Okay. So this is one way to solve this linear congruence. Okay. And this uses the concept of inverses. Okay. Now what if we have a problem like this? Somebody asks us to find a number, smallest number, which when divisible by one number gives us some remainder, when divisible by some other number gives us some other remainder, and so on. In other words, in mathematical terms, we want to find an x which is a1 modulo some m1, that same x is a2 modulo some other m2, and let's say we have n such congruences like that. Okay, now for this what we are going to use is what is known as the Chinese remainder theorem, explained here in English. Okay. So it says that if you have a set of congruences like this, a solution exists if m1 m2 mn are pairwise relatively prime. What does pairwise relatively prime mean? That in this group of n numbers, if I choose any pair, the GCD of those two numbers will be 1. Okay, so if I could choose m2 and m7 for example, the GCD should be 1. If I choose m21 and m1 for example, the GCD should be 1, and so on. Okay, so the solution exists. So solution is modulo m. What is m? So m is the product of all our m1 m2 up to m n. Okay, so the solution looks like this. So x, this is equal to a1 m1 capital M1 y1. We'll see what this means, up to an mn yn, where mk, this is equal to the product mn divided by mk. Okay, and yk, this is the inverse of mk modulo small mk. Okay, without stating the proof is straightforward, but let's see an example of that. Let's say that we have a number x, we say x is equal to 3 mod 5, and then x, this is equal to 4 mod 7, not equal to, congruent to. So x is congruent to let's say 2 mod 3. So in other words, what we are trying to find is, we are trying to find a number when divided by 5 gives the remainder 3, when divided by 7 gives the remainder 4, when divided by 3 gives the remainder 2. Now our first job is to check whether 5, 7 and 3, they are relatively prime or not. What is the GCD of 5 and 7? It is 1. GCD of 7 and 3, it is 1. And GCD of 3 and 5, this is also 1. So this means the condition is now satisfied. Now let's calculate m1. This is equal to 5 times 7 times 3 divided by 5, which is equal to 21. So m2, this is equal to 5 times 7 times 3 divided by 7, which is equal to 15. Then m3, which is equal to 5 times 7 times 3 divided by 3, which is equal to 35. And by the way, m is, our small m is just 5 times 7 times 3, which is equal to 105. Okay. Now we have to find y1, y2, y3. So y1, this is equal to m1 bar modulo m1. So m1 is our, which number is m1? 21. So 21 bar modulo 5. So we can easily see that this is equal to 1, because 21 times 1 is 21, and 21 when divided by 5 gives us the remainder equal to 1. So this is y1. Similarly y2, This is equal to, what is our m2? m2 is 15. So 15 modulo 7. 7, right? Yeah. Okay. So again, this is also equal to 1. Why? Because 15 times 1 is 15, and when 15 is divided by 7, we get the remainder 1. Okay. Now y3, this is equal to 35 modulo 35 modulo m3 is 3. Okay. So this is equal to 2, because 35 times 2 is 70, and 70 when divided by 3 is give us the remainder 1. So this is equal to 2. Okay. Okay. So our answer is x is equal to, okay. So let's write all the terms here. So a1 m1 y1 plus a2 m2 y2 plus a3 m3 y3. Okay. So which is equal to a1 was, okay, so a1, let's write them down, 3 4 and 2. Okay. So 3 here, 4 here and 2 here, and m1 was equal to 21 and y1 was equal to 1. Okay. m2 was equal to 15 and this was 1, and m3 was equal to 35 and this was equal to 2. Okay. So this is equal to 63 plus 60 plus 140, which is equal to 263 modulo 105, and which is equal to 263 minus 200, so 53 modulo 105. So all these numbers, 53 plus 105 is 158, 158 plus 105 is 263, and so on, are the numbers which satisfy the congruences. Okay. Now let's check. When 53, now go back to our problem here. So when 53 is divided by 5, we get the remainder 3. When 53 is divided by 7, we get a remainder 4, because 7 times 7 is 49, and then we get a remainder 4. When 53 is divided by 3, we get a remainder 2, because 51 is divisible by 3, and then we get a remainder of 2. So this is the way we can use the Chinese remainder theorem to find congruences like this. So this is it about linear congruences and their applications, and something about the Chinese remainder theorem. And you can appreciate that these kind of problems do occur in real life, and we are asked to find different remainders for different devices and so on. This is it for this video. Thanks for watching. Hope you like the video.